what we're doing today is we're going to finish off energy. Okay? So we're going to talk about 3 topics, and the class divides into 2 halves. So I don't know how it's going to go down. I'm very excited to see what's going to happen. It's sort of the highlight of my day to see how this shakes out. It's all downhill after that. So here we go. So there's 3 topics to cover on energy you haven't covered. One is power. Right. We have to talk about power because all the fun homework questions are about power. So it's really, in plain spoken words, how quickly, man, the quality of chalk is just, how quickly energy is transferred. And I'm being vague there because it means a lot of different kinds of transfer. But you'll see, you know it when you see it, or however that goes. Energy is transferred. It's just the rate of change of energy from one state to another. In joules is energy per second, or watts, which is in big W. Okay? So there you go. There's the unit. There's the hard part. So if it's how energy changes per unit time, then of course it's just the delta E, the change in energy, over delta T. The change in energy in some time. Or if you're talking about a specific process, what do we use? What do we do to something to change its energy? We do work. So you could also write it this way for a lot of problems. It's the work that you do, the external work you do on something, over delta T. The external work can be negative. It can be with what power do you absorb energy from a system. But that's really all it is. So in your mind, it's not really that complicated. So let's do a quick calculation. Let's see, we have a quick one, and then we have a not so quick one. Let's do a quick one just to get it in your head how to use this formula. Let's push, and I was going to say a block, but I forgot to get a block. So we're going to push a book against friction at constant velocity. We've done that many times at this point. We do it over and over. I don't even have a book. Where'd the book go? Oh, I guess I could have got a block, but I got the book. I found this book here when I came in. It's the one Dr. Stinson used. It's from the Harvard Classics 5-foot shelf of books. Okay? So if you ever think the adult world is intelligent and scary and you're nervous about entering it and we're all very serious, we're not. We're ridiculous, like egomaniacs, that we would own a book that is only about making your bookshelf 5 feet long. Okay? That's why it literally says that. That's what's valuable about this book, is it will make you look smart because it says Harvard Classics for 5 feet on your bookshelf. That's what we care about. Okay, so here it is. I'm going to push it at constant velocity. We've thought about the work I'm doing, but now let's think about the power. Here we go. Think about the power. Here it is. Oh, here's the book. I got to draw it differently. There we go. Ooh, there's an I. Oh my God, he has the 5-foot bookshelf from Harvard. Wow. FP. Okay, and now we're pushing it at constant velocity. And we actually don't care how far we push it. Before we would say, oh, let's push it from 0 to D and think about the work that we did. We could do that. Let's first think about the work. What was the work? If we push it from 0 to D, constant velocity, or constant force, well, both, what we did, we said, well, let's just draw the vector from 0 to D. That's like the displacement vector. And we said, oh, the work is just the dot product of those two. Remember, if you have 2 vectors, you need to multiply them and get a scalar, you dot them, right? F dot D, or magnitude F times magnitude D times a cosine between them, yada, yada, yada. But you could also ask, while I'm pushing that, how much work am I doing per unit time? What is the power of the push? What? Of the push. It is dumping energy somewhere. It's not speeding up the book, but it's going into what you heard about Tuesday, but into friction. So at some power, you're heating up the book and the table because you're generating, or you're pushing and making friction, or you're pushing against friction. So you just take that definition. P is the work over delta T. All right? And you say, what is the work? Oh, it's F dot D. F dot D over delta T. And then you say, does anything in here look like something in here? All right? So you say like that. And you say, oh, look at this. The displacement per time, that's just V. Okay, so the quick way to do these problems is to realize it's just F dot V. That's all you really need. Right, so the power is F dot V for if you have a constant force. And that's how a lot of the problems are solved. So in this one, we said if we pushed it at some velocity with some force, what's the power? Just multiply them. If they're in the same direction. Let's do a problem where they're not in the same direction.